Hello everyone, my name is Liu Xiao. I'm a research engineer from A-Star. Today I'll be presenting our work, Adaptive Visual Scene Understanding, Incremental Scene Graph Generation, co-authored with Nady Kandawal and Momi Zhang. Humans perceive diverse scenes every day and able to capture the objects and their relationships. Nowadays, computer vision models are able to perform the similar process by constructing a scene graph. This process is called scene graph generation, in short SGG. SGG enhances visual scene understanding by providing not only the objects but also their interactions, which is crucial for downstream tasks like VQA and image captioning. However, let's imagine this scenario. You pat and say goodbye to your tabby cat, then you leave home and drive to a mall, where you have your dinner there. This scenario involves three different types of scenes: home, outdoor, and dining. They're quite familiar to us, but for machine, this scenario continually involves new objects and new relationships in new scenes over time. To generate better on all kinds of scenes, machines need to retrain on the past scenes when they encounter the new ones, which becomes inefficient as data grows. So we need to teach machine how to learn incrementally, that is, learning only from the new data without forgetting the old one. Based on it, our team proposed a new problem, continuous scene graph generation, in short SEG. As the first team to explore continuous scene graph generation, we need to create our own benchmark. Specifically, we introduced three learning scenarios. The first scenario is relationship incremental learning, where new relationship classes added incrementally in 5 tasks. The second scenario is scene incremental learning. It is a harder task which simulates real-world demands for detecting new objects and relationships across the new scenes. When we encounter unknown objects, we might be still able to recognize their relationships. Motivated by it, we introduce the third scenario, relationship generalization. To address the complexity in SEG, we introduce our method replaced via analysis by synthesis. The goal of our method is to use symbolic replace to generate synthesized images in a balanced distribution for the next task. At task T, given trinity.tt, Rust store all triplets labels UT from previous tasks. These triplets are sampled, clustered, then filtered by a context checker module. This is to ensure text prompts we're going to generate are describing context-congruent scenes. Rust also adapts techniques to deal with long-tail distribution issue in the sampling process. Then Rust combines the selected triplets using the conjunction add to generate text prompts starting with the phrase realistic image of. Then Rust applies image generators such as Stable Diffusion to synthesize the scene images. Since Rust store only triplets instead of images, bounding box and triplets labels are required for the synthesized images, so we use the phrase model from current task to get the final exemplars. In general, Rust has several advantages. It removes the need to store images or annotation, thus addressing privacy concerns, and allows us to generate any numbers of data points for replay. In the experiments of scenario 1 and scenario 2, our method Rust outperforms all the SEG baselines with both backbone types. Compared to the baseline Rust ground truth, where we directly use scene graph labels from each task to create exemplars, we can see that decomposing scene graphs into smaller, diverse components with clear prompts is more effective. We also want to point out that Rust uses less storage and still outperforms the replay baseline. Although our Rust achieved the leading performance among all the baselines, its performance is still far from the upper bound. It suggests that it is still challenging for SEG models to learn new things incrementally. In scenario 3, as pointed out by the red arrows, we can observe Rust is more proficient in generalizing to classify known relationships among unknown objects. In this work, we propose the first benchmark to address continual learning in scene graph generation, covering 3 learning scenarios. We propose a new method using symbolic replace to generate synthesized images in a balanced distribution. We compare Rust against 8 baselines using 2 SGG models under 3 scenarios. This is the end of the talk. Thanks everyone.